Hello guys, this is Basim Rez giving you this recorded session on practice assignment 5 following lecture 5, which was on multi-key index. Throughout this session, we are going to solve 4 different exercises. Each would be tackling one of these 4 data structures, and throughout all of them, we would be employing or using and making an index on this table provided there. Afterwards, we will be solving one or more out of those 4 queries accordingly. Exercise number 1. We would like to construct a partitioned hash table as follows, considering that the hash value is to be constructed by concatenating the hash values of HD and the hash value of speed provided with the following tables. Consider that the hashed reference to the record to be the model value, meaning that, well, here we have got 2 tables, each corresponding to actually one of the hash functions, one for the HD and one for the speed. And here we've got the map actually as follows in the relation provided in the table. Then we would like to consider the hashed reference to the record actually to be the model value. So the model value would be in some sense like the pointer to the actual record. Afterwards, we will be solving this first query. Let's dig into. So here we've got the h of HD, meaning the hash function is the hash value of HD plus or concatenated with the hash value of speed. So how would this actually go? Well, we would go actually in our SQL table, in this table, model speed RAM HD, just line by line, row by row, entry by entry. So the first row, for example, was 101, 2.66, 1024, 250, and then we would calculate the hash for that. Then we put the hash in our table, and aside would be the model, which in this case would be 101. However, in a more cleaner way, actually, to have it written on paper, or like we have it actually here in this slide, we would go in just a different way around it. However, how would we work this out systematically? We would go through these rows from the original SQL table line by line. However, in this case, let's actually just go through the hash functions from the other side. Why? So we'd have actually the entries ordered instead of just going up and down through the hash model table. Instead, we would go actually line by line. So first off, we would search for an entry which has what? Which has 160 HD and 142 speed. And we can see here actually that this first entry right there, it's 1003, the model 1003. So accordingly, we would have 00 corresponding to the hash function of the hash value of 160 and 000 corresponding to the hash value of 1.42. So 0000 would be the hash, and the model corresponding to this one is 1003. Next step. So we go actually one row down in the speed hash. Let's see here. So you've got 1.86. Do we have actually an entry with HD equal to 160 and speed equal to 1.86? Well, we do. We've got here actually this entry, 160 and 100.86 for the speed. So how would we calculate the hash for this one? H of HD would be 00 and speed would be 001. So we add actually the hash here 00001 and the model would be 1011. Right? All right. Let's go on to the problem further. So here we've got 2. So do we have actually now an entry with HD 160 and speed equal to 2? Actually, we don't. So we go further. 2.1, do we have an entry with speed 2.1 while the HD is 160? We still don't. So we go further. 2.2, do we? No, we go further, 2.66. Do we have actually an entry with 2.66? No, but at some point actually we reach one that we have already in our SQL table, and it is 2.8. So we calculate the hash for this one, 00110, 00 for the hash of the HD, and 110 for the hash of the speed. We can continue those together, and we put it right there. And then aside would be the model equal to 1012. Great. One step forward. Actually, we would go on, and we find that we don't have actually the rest of those items. So we go by one further step in the HD, and we've got 200, and we take a look actually at the speed, and we don't have actually a speed with 1.42, while the HD is equal to 200, we have 1.86, and so on until we reach 2.2, where we do have one. So it's this row, it's this entry in red, and we would calculate the hash, which would be in this case 01 corresponding to the hash of HD, and 100 corresponding to the hash of speed. So 01100 would be provided then here in the hash column, and the model would be 1007. Then we go on until we reach actually another point that does exist in our table, and then we have actually 2. So 2, while 250 would be what? 10010. 10 for the hash of HD, and 010 for the hash of 2 speed. And so on, and so on. So it'll be something actually for 108, for example, 2.2, where we do have actually the 250 is 10, and the 2.2 is 100. So it would be 1010 provided then. And we've got actually before this one, the 21.1. So of course, we'd have this one previously, and it would be 250, 1011 corresponding to 2.1. Okay. We go further. We've got actually the 1002 with 2.1 speed, and then 2.2 speed, the one we just solved, 108. All right. Then we've got these three. So 2.66, 2.8, 3.2. So 2.6 is the first one. So 250 equal to 10, 2.66, hash of that would be equal to 101. Okay, so that would be 10101. Then the one afterwards, 10110, and then the one afterwards, 10111, which corresponds to then to what? To 105 right there. All right, and then we've got actually those two left with HD equal to 300. We would solve the first one where the speed is equal to 3.2. No, not this one. The first one would be 2.8 because it comes first. So then this one would be 11110, and the other one would be 11111. All right. So we've got those actually provided the model, which would be our reference. And are we done in this case? Actually, would this be the actual table, hash table at the end? Would this actually be the partitioned hash table? Is this the complete one? Actually, no. Why? Because then the hash value would be our address. And in this case, what about actually the other entries in between that have an empty model that's not referring to anything? Would they still be existing in our physical memory? They would. And accordingly, actually, because we're just solving this by paper, so we have got it this way. However, we could have at the beginning had actually the hash column already initialized for every value. So that would be 0000, then 0001, then we would be having a lot of other entries, then 00110, and then we'll be having a few more entries, empty ones, then 01100, then 01101, and along the others afterwards, while actually empty at the model column, and so on, 10010, 1011, 101100, and so on till we reach 10111. Then we've got few more rows where there is a hash value actually, but then the model actually would correspond to an empty entry, as it's not actually pointing to anything at the point. and so on till we reach the 1111. Hence, we do have now actually our complete data structure, a partitioned hash table. Well, let's now solve actually the first query for an exact value query, but then we've got actually two search keys, speed and HD. And our index actually worked this out, having included the speed and the HD. So in this case, 2.2. If we're looking for this one, we're looking for the speed 2.2. So we calculate the speed for 2.2. 2.2 is equal to 100. What about actually the HD? HD equal to 250. That means that the hash value of HD would be 10. Hence, the complete hashed value in our partition table would be equal to h of HD, which is 10, plus h of speed, which is 100. Hence, we have 10100, which is this one right there and highlighted in green.
Exercise number 2. We would like to construct a grid index on the SQL table that we have, considering the reference to the record to be here as well, the model value. And afterwards, we will be solving this range query right here. So to construct a grid index, we would construct a table in this shape on the right side. And in this case, we'd like to have our grid index on the hard drive and the RAM. Why? Because we'll be solving actually this query. RAM and HD are the search keys provided. So how many columns and how many rows would we have in such table in this data structure, a grid index? That depends on the number of unique values in our original data table, in the RAM part, as well as actually in the HD column. So if we take a look here, we'd have actually 3 unique values. And if we would have a separate row or actually a separate range for each of these values, we would have then 3 rows. Accordingly, we'd have 512 and 1024 and 2048. What about the hard drive? Well, we would count the unique values in hard drive as well. And in this case, we have 160, 200, 300 in purple, then 250 in orange. So those will be mapped in our hard drive. And in case we'd like to map each one of those to a unique or a separate column, then we would have actually 4 columns. Great. Afterwards, we'd go through these entries, models, one by one, and actually we refer back to the model to enter this as the reference to our data table. So, for example, let's take a look at 1001. We have a RAM of 1024 and an HD of 250. So we go to the row of RAM 1024 and we go then on this row to the column with HD equal to 250. So that will be this one. So we insert 1001. Next step, we go to the next row, 1002 model. So 1002 model exists in supposedly in 512 RAM and 250 HD. So that would be actually the place to refer to this row with the model 1002. Next, 1003. We've got RAM 512 and HD equal to 60. So we go to the row in the grid index table, 512, and to the column with 160. We insert 1003 as a reference. Next entry, 1004, with a RAM 1024 and HD equal to 250. In this case, you would just add this as well along 1001. So we have now 1004 inserted in this cell. We go one more step further and we have 1005 inserted in column 250 with row 512 cell. Then we go to 1006, 1007, 1008 to be inserted accordingly. So, for example, you would have 106 inserted in supposedly RAM 1024 intersecting with HD 300. So that would be on this part. What about the next one? 1007 should be in 2048 intersecting with 250, supposed to be right there. Then what about 1008? It should be in 2048 intersecting as well with 250. Or, oh yeah, and 1007 supposedly 1024 intersecting with 200, so it would be right there. So we got these three entries now indexed in our grid index. 1009, where would this one be inserted? 1024 intersecting with 250. 1010 should be in 2048 intersecting with 300, so it'll be right there. And 1011, so we've got 1011, it should be at 2048 intersecting with 160, so we'll be having 1011 right there, and 1012 would be in 1024 intersecting with 160, it would be right there. Okay, so we have at the end, actually, this would be our final state of such grid index, indexing every entry from the original data table. At this point, we would like to actually solve or execute this query. So how would this execution look like? So actually, at this point, if we're going to select just SAR from PC, from this data table, we would be getting every entry from the table. However, we are specifying a range in this case where RAM greater than or equal to 1024 and the hard drive less than or equal to 200. So first part is RAM greater than or equal to 24. So that means that we would be selecting from 1024 and up from there. So we'd be even going with 2048. So in this case, it would be something like that. Then we can kind of limit our output or add one more constraint to this outcome by specifying that the HD is less than or equal to 200. That means that we would be accounting just for this column 200 and the columns before it. In this case, it's just 160. So it'd be this. And accordingly, this would be our outcome. We would go to this part of the table and we would retrieve actually the actual data records of the models 1012, 1007, and 1011. Exercise 3. We would like to construct a KD tree for our data table provided. And this KD tree would be on speed, RAM, and HD on this specific order, where we would have the bucket size specifying that it can hold up to 2. It can refer actually to 2 records. And in case of a full bucket, a split is performed using the mean average of the 3 values in hand. So once we have actually an additional point or additional entry to index, and the bucket size is not enough anymore, we have a third one, so we calculate the mean average of the 3 values, assuming that the records are inserted sequentially and in orders. So we're inserting our records as per the appearance in the actual data table. Afterwards, we'll be solving this query. All right, so let's dig in. So first, we'll have our first entry in the table, 101. How would this be inserted? Just a bucket and having 101. All right. What about actually the second entry? We go on and we add also 102. Our reference here is 102, referring to this second row in our data table. Afterwards, we'd like to insert 1003. However, there is a problem. If you remember, actually, from the previous slide, we have actually a constraint in our design here where our bucket size can hold up to 2 records. But this 1003 would make our third point for this bucket at this case. Hence, we would like to now go on and split this node or this bucket into 2. And afterwards, we would calculate the mean average actually between these 3 records to have our point on the upper level. How would this point look like? Let's see. So here, as we said, we would be going to have our index on this specific order: speed, then RAM, then HD. So first, we take in consideration the speed. So as we take in consideration the speed, and we're having 1001 and 1002 and 1003 records, we would be taking only the speed 1.42, 2.1, and 2.66, adding up all of those and dividing by 3, taking the mean average. That would be equal to 2.06. So our node at this point would differentiate between the new 2 nodes or new 2 buckets according to this value, speed of 2.06. So on the right hand side, what would we have? Now we're having 101, 102, and 103 should be placed in these 2 new buckets. So first, 101, where should it be placed? On the right or on the left? 2.66 is greater than 2.06. Hence, the model 101 would be referred to in the bucket on the right hand side. What about 102? 102 having a speed of 2.1, still greater than 2.06, so it would be referred to as well with the bucket on the right hand side. 103 then would be placed on the left hand side because 1.42 speed of this entry is less than 2.06. Great. We go further to the fourth entry, 104. So 104, we're having a speed of 2.8, right? And then our first node is taking consideration the speed, and the speed is 2.06. So we should be going to the right hand side, to the subtree on the right hand side. And then we're having a problem. Now 104 should be placed in this bucket. However, if we remember, the bucket size can hold up to 2 only. So we would be dividing this bucket at this point. So how would we divide it then? We divide it and we take the mean average of the RAM values. Why in this case? Because now we're taking our index in this order of consideration: speed, and then RAM, then HD. We already considered actually speed above, so we'll be considering at this point RAM. So we have 101, 102, and 104 to be placed. And we take in consideration the RAM, so 1024 plus 512 plus 1024, all of those added up, dividing by 3, taking the mean average, we'd be having 853. RAM 853 are here referring to the RAM values. Then 101, where would 101 be placed? It has a RAM of 1024, which is greater than 853. Hence, 101 would be placed on this right bucket. What about 102? It has a RAM of 512, less than 853, so it would be placed on the left. 104, finally, has a RAM value of 1024, which is greater than 853, so it'll be placed on the right. Looks good. Then we go to model 1005 record. So we have 1005, and as we start, we are at this node, which is taking in consideration speed 2.06, and our value of 1005 for speed is 3.2, which is greater than 2.06. We go to the right, sub 3. Now we're taking in consideration the R, the RAM, R 853, while our 1005 is 512, which is less than 853. So we go to the left, and 1005 should be placed along 1002. Then, right? Yep, right. Then we go one step further to model 1006. 1006 should be placed in this bucket. Why that? Well, S2.06 is less than 3.2, so we go to the right. Then 853 is less than 1024, so we go also again to the right. And then we are at this point. 1001, 1004 already exists in this bucket, and it can hold up to 2 only. So to make this work, we would split this bucket. And we would split then, and we calculate the mean average of what? Of the HD. Why that? Because we are taking in consideration those index C's, or this index, or these values for our index in order: speed, then RAM, then HD. And at this point, we already calculated something for S, recalculated something for R. So at this point, we should be calculating for HD. So 1006 will be placed right there after we split this bucket into 2. We calculate the average of HD, 300, 250, and 250. All of those added up over 3, 267. So 101, this model would be placed on the left-hand side. 250 is less than 267. 1004, 250 still less than 267 on the left. But 1006 will be placed on the right because 300 is greater than 267. Good. Then 1007. 1007 having a speed of 2.2 greater than 2.06. Then a RAM of 1024 is greater than 853. So we go to the right. Then 200, which is less than 267. So we should go to the left. However, we don't have enough space there. So what would we do? We split this into 2. But then what is actually the node which would be taking in consideration? What are the value which would be taking in consideration, or from where? From which column? At this point, well, for speed, why? We take in consideration the speed. Then we took in consideration the RAM. Then we took in consideration the HD. At this point, we come back actually in this order back to speed. So we take 2.66, 2.8, 2.2, the speed values of these 3 rows from three records, and we add them up over 3 to 0.55. 101 is 2.66 greater than 2.55, so on the right. 104, 2.8, which is less than or greater, still greater than 2.55, so we put on the right. 2.2 less than 2.55, so we put it on the left. So 107 on the left and 101 as well as 104 on the right. 1008, and this one should be placed right there, and we have enough space for it, so it would just be put. What about 1009? 1009 having a speed of 2 less than 2.06. We go to this side and we have actually enough space for it. So 1009 will be placed just like we can see right here. Then 1010. 1010 having a speed of 2.8, which is greater than 2.06. So we go to the right. A RAM value which is 2048 greater than 853. So we go again to the right. Then hard drive value of 300, which is greater than 267. So we go to the right, and we have enough space for it. There is a spot, so we add it there. 1010. Then we go to 1011. All right. We would have a problem with 1011. Why that? Well, 1011 having a speed of 1.86. 1.86. So you go to the left, and then actually right here, we don't have a spot for 10, 11. So what should we do about this? We split this into 2. And which value would we mean average and take in consideration actually to differentiate between these two no buckets at this point? Speed, RAM, or HD? RAM. Why? Because up there we consider the speed. So in order, at this point, we should be considering RAM. So you take in consideration the RAM values, we add them up, and we divide by 3, take the mean average, equal to 1,195. 1,003 would be put onto the left side. Why? Because 512 is less than 1,195. 1,009 is having a RAM value of 1,024, which is less again than 1,195. So 103 would be here along 109, but 1,011 would be on the right hand side because its RAM value 2,048 is greater than 1,195. Looks good. What about 1,012 then? 1,012 should be put right there, right? We don't have space for it. We don't have actually enough space for it. So what will you do about this? We split this one into 2. So at this point, we should be taking in consideration what? We just considered speed. So at this order, we should be considering RAM values. So considering RAM values, 1,024, 1,024, 1,024, add them up, divided by 3, you have 1,024. Well, because all of these RAM values are exactly the same for the 3 records, we have a problem now. Why? Because now we wouldn't be able to differentiate between 2 new buckets. In this case, if we have the RAM value 1,024 is our value of differentiation. So what will we do about this? We go on actually and consider the next column value in order, which supposedly HD, speed, RAM, HD, speed, RAM, HD. So this one would just point to another node, which would be a hard drive value. Then we add up 250, 250, and 160. So adding those up, we would have 220 after actually taking the mean average. So then 101 would be placed on the right hand side because hard drive value is 250 greater than 220. 104, 250 hard drive value would be on the right hand side. So we put it right there along 101. What about 1,012 finally would be placed actually on this left bucket because 160 is less than the hard drive value of 220. At this point, we can actually differentiate between the 3 records. All right, so as we are done with building our KD tree, now we'd like to execute this query right here. So how would this actually be executed systematically through our software, our database management system? So select start from PC where speed greater than or equal to 0.10 and speed less than 2.5 and RAM greater than or equal 1,024 and HD less than or equal 230. So first, we are at the root node, which is considering speed 2.06, right? So we take a look at the search key speed in our query. So we have speed greater than or equal to 2.10 and speed less than 2.50. So for sure, we know that our answer, if it exists, it would be on the right-hand side sub-tree. So we go to the right. Then we are, at this point, considering RAM value 853 to differentiate actually between our subtrees. So we take a look, or we look for the RAM in our query. RAM is greater than or equal to 1,024. So that means that our outcome should be retrieved from the right-hand side subtree. This one. Okay. Then at this point, we're considering hard drive value. 267 is our value of differentiation. So we look for the hard drive value in our query, and hard drive less than or equal to 250 is our range actually, or our constraint in this case. So 250 is less than 267. So we should go to the left side subtree. So we are at this node now. Then what? At this node, should we go left or right? We are considering speed at this point, and the speed is 2.55. And here we got speed in our query should be greater than equal 2.10. Well, 2.55 is greater than 2.10. And the speed is also less than 2.50. So as 2.55 is not actually less than 2.50. So hence we know that we should go to the left side subtree, which would contain then this bucket 107 and 1008. And here, this one would be our records in the outcome of such query. Exercise 4. Here, we would like to construct a bitmap index for our data table. And the index would be on for the columns speed, RAM, and HD, just like our previous exercise. But in this case, we would build a bitmap index instead of a KD tree. And afterwards, we would go on and execute each of those 4 queries. So let's dig into it. So to build a bitmap index, we would need to construct a table, an index table for each column that we are having our index on, speed, RAM, and HD. But then, how many rows will we have, for example, in the speed index table right there? Or how many rows will we have in the RAM index table? What about the HD index? Well, that depends on the unique values in our column. So how many unique values do we have in the speed? How many unique values do we have in the RAM column? How many unique values do we have in the HD? So as we can see here, a clear one here would be the RAM. We have 512, 1024, and 2048. So we've got 3 unique values. Hence, we will be having 3 rows in our RAM index table for our bitmap index. For the HD, 250, 160, 200, and 300. So there are 4 unique values. So we'll be having 4 rows. And same case for the speed. So let's start actually with speed. How would our index be calculated? Well, 1.42, where does it exist in the actual data record? 1.42 in this record only. So 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0. Hence, our index would be as following. What about 1.86? So 1.86 would be all zeros up to the 1 before the last one, 1, 0. What about 2? 2 would be 0, 0, 0, 0, 0, 0, 0, 0, 0. Not 0, this would be 1 because here is 2. Then 0, 0, 0. And so on. So for example, let's take another one, 2.66. It exists in the first record only, so that'd be 1, and the rest are zeros. What about the RAM index? Let's see. So 512. Where does 512 exist? Right there, right here, and again here. So 0, 1, 1, 0, 1, and the rest are 0. 1024, 1, 0, 0, 1, 0, 1, 1, 0, 1001. And same for 2048. We would count actually just the ones that does have 2048 as ones and the rest are zeros. And finally with HD, we'd be having for 160, for example, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0, 1, 1. And 200 would be all zeros except for this one, and so on. All good? We go forward. So that actually would be our bitmap index, consisting of or composed into these three index tables. Then let's try to execute our 4 queries one by one. So first one is the exact value query, speed equal to 2.2 and HD equal to 2.50. So speed equal to 2.2. So where have we got actually the speed in consideration for the in this speed index table? So speed equal 2.2, so it should be this index, right? What about actually HD? 250. So we go to 250 right there. Then we are ANDing those together. So we would be ANDing the index of both the vector, the bit vector of each would be ANDed together. So we'd have actually this. What does this refer to? It refers actually to the number of record which actually abides by both constraints in this case. So 0, 0, 0, 0, 0, 0, 0, 1, meaning that 1, 2, 3, 4, 5, 6, 7, 8. So 8th row in our data table. Let's go to it, and it is actually 1009 or 1009. Correct. Next query, a range query in this case. A RAM is greater than or equal to 1024. So we've got the RAM 1024 and whatever greater than that. And the HD is less than or equal to 200. So HD is less than or equal to 200. So this one and whatever is less than that. So these are actually the ranges which we would take in consideration. Then what? We would OR together actually the bitmap vectors of the RAM here, because we are looking for this whole range, and we would OR the bit vectors for this 2 HD values or these 2 HD rows, because we are looking for this whole range, and then we would add the outcome of ORing the RAM bit vectors together and the OR of HD vectors together. So here we've got 100, 10, 1101, and the other one referring to this of the RAM, and here 001 zeros up to 11 right there for the HD. Those are ORed together, and those as well are ORed together. Then we would AND the outcome of both to get actually the intersecting actually records which satisfies both constraints. Supposedly these would be actually our entries from the original data table: 1007, 1011, and 1012. Good. Then here's our third query. Also considering range, but more constraints actually. Speed greater than or equal to 2.10, so this one and whatever we have afterwards, but it's less than 2.50 strictly, so it would be actually up to this point only. We OR those together right there, we OR them together. Then we have actually for the RAM is greater than or equal to 1024, so 1024 and whatever greater than that, we OR also those together, would be the outcome. And then we have actually for HD is less than or equal to 250, so 250 and whatever less than that, so we OR all of those together. these 3 bit vectors, we get that. And then the outcome of these 3 equations would be added together according actually to what was mentioned in the query above right there. So we have actually this intersecting record satisfying all of the constraints all together. We look forward to get them actually from the data table, and here they are: 1007, 1008. And the 4th query here, we would also look for range. However, we have actually or as well as an and in our where statement in the query. So actually we would go and execute the and first, then we would have the outcome ordered with whatever we have for the speed. So for the speed less than or equal to 2.8, we would have the whole range 2.8 and whatever less than that, and RAM strictly less than 1024, hence just the 512 index vector right there. And for the HD less than 300, we have actually strictly less than 300, so 250 and whatever less than that. Then we would OR all of those from the HD. We would have actually just the bit vector for the RAM on its own, and we OR all of those for the speed, all of the bit vectors. And to execute the AND part first, we would consider ANDing the bit vector from the RAM index with the outcome of ORing the bit vectors from the HD index. And that would be actually the outcome right there. Then we OR that with the outcome of ORing the bit vectors from the speed index to have this resulting bit vector accounting actually for the whole query. Accordingly, actually, we would consider every row from our data table, every record except for 1006, which does not satisfy our query constraint. And this was it for this session. Hope you got something, and refer back to the lecture whenever you have questions referring to the concepts of these data structures.